Hey everyone, we're going to continue studying bases. Up to this point, it might have looked, when I found a basis for a particular subspace, that it was kind of a haphazard process that I was going through to identify bases. What we're going to learn today is a way that will help take some of the guesswork out of identifying bases. So let's get started. So let's start off with a matrix. So let's let A be an M by N matrix. And I guess we'll put two parts to this definition. So part A, if the columns of A, so if let's say C1 up through C sub M, N, are the columns of capital A, then we're going to define a certain subspace of Rm. So this is going to be, let's say it like this. So then the span of C1 up through C sub n is called the column space of capital A, and it's denoted COL of A. Right? Remember, anytime if you have a collection of vectors, the span is a subspace. In this case, each of these vectors has M entries, so the span of this set right here is contained in, it's a subspace of R sub M. Right, so col A is a subspace of R sub M. There's a second one. So the null space of A, denoted NULL of A, is the, how do I say this? It's the solution space. So the set of all possible solutions. So the solution space to the homogeneous system AX equals 0. We've shown earlier that this subspace consisting of all x that satisfy this equation, we've already shown that it's a subspace. We're just giving it a name here. It's called the null space. Right, so let's just say note col A is a subspace of Rm, and null A is a subspace of Rn. Now, I've done a few examples of finding bases for null A. I didn't say the words null A, but I've shown how to find a basis. I'm actually going to write out the procedure so that take all the guesswork out of it, and we're also going to develop a procedure for finding a basis for the column space of A. Now, before we do that, let's see why the column space might be important. So let's see, suppose that we have the system AX equals B. Now suppose this is consistent. Right, so there is at least one vector X out there that solves this equation. Now if we write the vector X, that's going to be a, if we keep it, A is M by M, then this would be a X1 through Xn. And do I need to write out B? No. Then we have, so remember, when we do matrix multiplication, A times X, we can view it as first entry of X times first column. We haven't really thought about this for a while, but early on when we were talking about matrix multiplication, one way to think of matrix times column vector is first entry of X times first column plus second entry of X times second column, and so on, dot, 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 down to X sub n times C sub n equal to B. In other words, what does this tell us? This is consistent, or when it's consistent, what we have is that B can be expressed as a linear combination of the columns of A. In other words, B lies in the column space of A. And so, B is in the column space of A. And this argument reverses also. If B is in the column space of A, then it can be expressed like this, which tells us that this system is consistent. It tells us exactly who A solution would be. So let's write this as a theorem then that totally captures what it means for this original matrix system to be consistent. So theorem AX equals B is consistent if and only if B is in the column space of A. Right, so that tells us why we might be interested in the column space of a matrix, right? It allows us to get a feel for when our system is consistent. So we want to have a good description of the column space of A. In particular, it'd be nice if we have a basis for that particular subspace. So we're going to write down a procedure now, and let's say finding a basis for column space of A. So we start off, so we've got our matrix A, and I want to express it in terms of columns. So we've got C1, C2, dot, 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 Cn. So here's my matrix A written column by column. Column 1, column 2, all the way down to column N. Now what we're going to do is we're going to get it into row echelon form, and so let's say call them D1, D2, up through D sub n. So this matrix, which I guess we can call it B, this one is in, we don't have to go all the way to reduced row echelon form. All we need to do is get into row echelon form by doing row operations. All right, so there's step one. Start off with a matrix A, do row operations to arrive at a matrix B who is in row echelon form. Now, once we have our matrix in row echelon form, we can identify which of the columns are pivot columns. Right? So let's say identify the pivot columns. Now, remember, pivot columns are pivot columns, right? I mean, if row 2, or sorry, column 2 is a pivot column, then column 2 of A is a pivot column as well. And so we want to identify the pivot columns of A. These form a basis for the column space of A. So here's the important part. To identify the pivot columns, you need to have leading ones, right? So you got to take it out to row echelon form, identify the leading ones, or find the leading ones, and those columns of B are pivot columns. The corresponding columns of A, not B, of A form the basis. All right? So for example, if you're trying to create the basis and you happen to see, oh, column number 3 of matrix B is a pivot column, then you will take column 3 from A and put that into the set that will be the basis for your for the column space. So let's try an example. And what we're going to see now is that this is going to allow us to identify bases anytime if we have some collection of vectors in Rn. And we say, okay, let's think about the subspace that is the span of these vectors. We will be able to use this process right here to find a basis for the span of any collection of vectors. And so that's how I want to word this question. So let's let W be the span of the following collection of vectors. 0, 2, 1. 1, 3, minus 1. Minus 1, 2. And 1, minus 1, negative 3. Got that right? Yep. Okay, now the instructions, what I'd like to do in this example, I want to find a basis for W. All right, so we have this collection of 4 vectors sitting in R3. W is the span of those 4 vectors, and I'd like to find a basis for the span. So what do I do? Well, I'm going to set up a matrix. And so I can think of these vectors right here as the columns of a matrix. So 0, 2, 1, 1, 3, minus 1, minus 1, minus 1, 2, and 1, minus 1, minus 3. Okay, so if I can find a basis for the column space of this matrix, then I have found a basis for W, because W is the column space of this matrix. So you do some row operations, and I won't make you go through them. I worked it out, got it in row echelon form, and it looks like this. So I'll tell you row by row. 1, minus 1, 1, 1. 0, 1, minus 1, 1. And 0, 0, 0, 0. So I did row operations, got this. Notice this is not reduced row echelon form. Row echelon form is fine, right? I can see that I got a leading one in the first column and a leading one in the second column. So these are pivot columns, which means that my first 2 columns of the original matrix are pivot columns. And those 2 columns are a basis for W. So this, you can see now, this process takes all the guesswork out of it. It tells us exactly which columns are redundant, which vectors are redundant. It tells us we don't need these 2. If we want to talk about the span, all we need is the first 2. So this set right here, 0, 2, 1, 1, 3, minus 1. This right here is a basis for W. Remember to go back to the original matrix or the original collection of vectors. Don't choose these. These 2 right here are not a basis for W. They don't even live in W necessarily. Right? When you do row operations, it actually changes the column space. Each time the column space will change. It's the pivot columns of the original matrix that you want to form the basis. All right, so now let's move on to our study of the null space and finding a basis for the null space. And so before we actually get there, I want to think about something that we actually saw on the first quiz, and it was kind of mysterious for some people. I want to work through this. So suppose that I'm going to call it x sub p is a solution to the linear system AX equals B. I'm calling it x sub p. P stands for particular, right? So it's a particular solution. And let let's say V1 up through V sub k be a basis for the null space of A. So remember, that is the set of all solutions. The null space is the set of all solutions to the homogeneous equation AX equals 0. Okay, so if I choose anything in the null space of A, so let's say letting, I'm going to call it X sub H, H for homogeneous, equal A1 V1 plus dot 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 plus A sub K V sub K. So this is a solution to the homogeneous system, right? Because it's a linear combination of a basis for the null space of A. Observe that X sub P, let's do it like this, A times X sub P plus X sub H is equal to AX sub P plus AX sub H, just using the distributive property here. That's equal to, so let's see, X sub P is a solution to this one, so this is equal to B. X sub H is a solution to the homogeneous equation, so that's a 0 vector. Right, so it's equal to B. And so what we just showed is that every vector of the form X sub P plus X sub H is a solution to the original equation. Right, so every solution to our original equation can be expressed as particular solution plus solution to the homogeneous equation. So let's write that out. So theorem. So if X sub P is a solution to the linear system AX equals B, then every solution is of the form X sub P plus X sub H, where X sub H lies in, I'm going to say that, yeah, just say it lies in the null space of A. Right, so to capture every possible solution to this original equation right here, what we can do, if we happen to know one solution, and we're able to figure out who all the solutions to the homogeneous system are, then we know all the solutions to this equation right here. So that this tells us why we might care about finding a basis for the null space, right? Because that allows us to tell exactly what all the X sub H's look like. They look like linear combinations of the basis for the null space. Now, we've already done, we've already seen how to do this, so I'm going to write down, though, finding basis. So let's see, finding a basis for the null space of A. So number one, write out the general solution to AX equals 0 in terms of parameters. Okay, so we've seen this before. If you have this equation right here, do your row operations, and what do? You identify the free variables, and for each free variable, we give it another parameter. I call them usually S and T. There might be more than that, R, S, T, and so on. So you write out the general solution in terms of the parameters R, S, T, etc. So there's step one. Step two, separate that general solution into its parameter components. So let's say separate solutions. So separate the solution by parameters. I'll do an example and hopefully you'll see what I mean. I've already done this a few times though, but separate the solution by parameters. And then factor out each parameter. So factor out parameters. The remaining vectors form the basis. So the remaining vectors form a basis. Okay, so there's the steps. I'm going to do an example now so we can see this in action. In fact, I want to see the entire theorem in action. So here we go. Let's let A be the following matrix. I'm going to go row by row, 1, 2, 0, 1, 0. 1, 2, 0, 1, 0. Next row, 0, 4, 1, 0, 1. 0, 4, 1, 0, 1. And then 1, 6, 1, 1, 1. 1, 6, 1, 1, 1. All right, so we've got a 3 by 4 matrix. Also, I need a vector B, and B will be 1, minus 1, 0. Okay, now the instructions here, I'd like to express the solutions, so the entire set of solutions, express the solutions to the equation AX equals B as, let's say X equals X sub P plus X sub H, where X sub P is a solution, well, let's say a particular solution, and X sub H is in null of A. All right, so I'm going to set up an augmented matrix. It'll be the augmented matrix corresponding to this system right here. So it'll be a 1, 2, 0, 1, 0, 1. 0, 4, 1, 0, 1, negative 1. 1, 6, 1, 1, 1. Wait, 1, 1, 1, yeah, 0. Okay, so there's the augmented matrix. And if you go through the row operations, here's what you end up with. So it's going to go, it's got some fractions in here, unfortunately, but that's okay. Um, 1, 0, negative 1 half, 1, negative 1 half, and 3 halves. 0, 1, 1/4, 0, 1/4, and negative 1/4. And then I've got a row of zeros. 0, 0, 0, 0, 0, 0. Okay. So now, I'm going to put a little line here to remind us that's where the equal sign is. We've got 2 leading ones, which means that we've got 3 free variables. So let's write these out as, so x3, let's call r. x4 is going to be s, and x5 is equal to t. And then we have x1 is equal to 3 halves plus 1/2 times r minus s plus 1/2 t. And x2 is equal to -1/4 minus 1/4 r minus 1/4 times t. Okay, so the general solution then looks like this. Okay, so x1 is going to be 3 halves plus 1/2 r minus s plus 1/2 times t. And then we're going to have a minus 1/4 minus 1/4 r minus 1/4 t. Then we'll have an r, s, and t. And so now I'm going to split this up in the following way. So I'm going to have a 3 halves -1/4 0, 0, 0. Plus, so what I want to do, I'm going to separate this in terms of parameters now. So we're going to have plus 1/2 r -1/4 r r 0, 0. Now the stuff that involves s is going to be a -s 0, 0 s t, and then the last piece -1/2 t. Oh, sorry, that's a positive 1/2 t. -1/4 t 0, 0 t. Okay, now I'm not quite done. Let me take this one step further. So this is equal to 3 halves -1/4 0, 0, 0. Plus, now I'm going to pull the r out of this first vector. So this will be an r times, and you've seen me do this before, pull the parameters out. 1/2, -1/4, 1, 0, 0. Plus, now I'm going to pull the s out of the next piece. Ooh, why do I have a t here? Sorry, that should be a 0 in that one vector right there. Right? It should have been -s, 0, 0, s, 0. Yeah, sorry. S times -1, 0, 0, 1, 0. Plus, now I'm going to pull a t out of the last piece. 1/2, -1/4, 0, 0, 1. Okay, so now let's see what we have. My particular solution, x sub p, is right there. The solution, really all possible solutions, the x sub h is right there. So what we have then, here's my particular solution, plus all possible linear combinations of those 3 vectors, that's the r, s, and t, all possible linear combinations give us all possible solutions to the homogeneous equation. In other words, the vectors, these three column vectors right here, form a basis for the null space of A. All right. Okay, so that's a good place to stop here. I will see you next time.